In this third lecture of optics, we will look at another aspect of light, which is the wave nature of light. So we will start with looking at the interference of monochromatic waves. Then we go to the effects of coherence, analyze the interference of plates and wedges, Young's interferometer, and Michelson interferometer. All will be topics. Okay, so what is interference? Well, you have here an example of water waves. So you see these droplets, they are dropping into the water at pretty much regular intervals, and every drop causes a disturbance in the water, and then you will see waves running outwards. And of course, if we have two such similar sources, they will start to interfere, and as indicated here by the black circles, you will see interference patterns. So of course we will have to sort of analyze over time what happens, and there are certain positions, for example these lines here, where there's basically no distortion and the water is pretty much at its original position, and in other places like here there would be quite vigorous movements of the water which would correspond in light to high intensity. So we would have destructive interference, i.e. low intensity, and constructive interference, which is high intensity. So we will now look at this phenomenon by some first experiments. This is a device that simulates water waves. So there's a light source here, a generator of the waves here, a mirror behind that you can't see that then generates a pattern of white and black fringes on the top, on the front here, as you will see later. So I want to show you first here a zoom in to this place here. So you see that there's a little pin that generates the water waves on the surface of the water. If I touch here, you see this is really water. And then if we show to the front, you now see here how the waves are generated. So the trick is, of course, the waves are much faster, and to show them this nice and slow, we are using a stroboscopic technique. That means that there's a slight frequency difference between the light source and the frequency of the water waves, so that you get this feeling of slowly running water waves, but it allows you to see them really nicely. So this is the technique of stroboscopy, or it can also be called heterodyning. So as you see, this is now a nice circular wave, and in the next view I will show you what happens if we have two circular waves and they start to interfere. So now we've added two sources rather than one source that had a circular wave. Now we have two circular waves, and if we zoom in, we see here the first emitter and the second emitter. And of course, they are coherent and in phase. See how the waves are running outside. So now the interesting part is that you see now the interference of these two water waves. And if you look here, you see a line of destructive interference where the water waves cancel each other. And here, that's a line of constructive interference where you have the maximum amplitude for the interfering waves. And interestingly, these lines, as you can see, follow a hyperbola around these waves, as we've seen in the theoretical slide. So next, we're going to go on by adding more emitters to see what happens if you have the interference of several emitters. In the previous experiments, you have already seen this effect of interference. That means that water waves with a lot of agitation can overlap with another water wave with a lot of agitation, and as a result you get no agitation of the water. That means no movement, and that would translate to no intensity in the case of light. But is that really true? So we're going to look at this effect much more in detail now with one of the most interesting experiments, which is the Michelson interferometer tuned to darkness so that you can actually block a part of the light and it becomes bright. Very fascinating. Okay, this is a Michelson interferometer, and I want to show you one of the most interesting experiments, I think, in optics, the fact that light plus light can actually give you darkness if it is coherent light. So the Michelson interferometer you see here, and if we look from the top, you see a laser here. That laser generates a laser beam. Here it is a telescope that makes the laser beam nice and wide and parallel. And here's simply a baffle, an aperture where I can limit the field that we want to see and that we send to our Michelson interferometer. This, of course, is the beam splitter, so that part of the light goes this way and then to the screen, and part of the light goes this way and then to the screen. So now, when we look at the interference pattern, you see a series of fringes, and often you see circles. That is when the Michelson interferometer is misadjusted. Now it's adjusted relatively well, but as you see, we still see stripes. Ideally, we could see a completely bright or dark screen depending on what path difference we have. We don't see that because the mirror probably has a little bit of astigmatism, a tiny little bit, 2 or 3 wavefronts of error, basically, and that's why we still see the fringes. So what I'm going to do now is, you see here I have a black piece here, and I'm blocking part of the beam, and you see now when this part is blocked, then the fringes disappear, and here they are in there again. So I can decide whether I want to have interference or not. And now we're going to try the most fascinating experiment. I'm limiting the baffle, making this smaller and smaller and smaller. And then we are waiting for the moment that we just have darkness, which means that at that moment, light and light will actually give darkness. And when I then put in this baffle, as you will see, then I can make it brighter. Isn't that interesting? We block light, but the result is more light. So let's wait for the moment when this happens, when the dark fringe is really blocking the whole beam, basically. I block one side and it becomes bright, dark, bright. So you see, light and light can give you darkness, which is less bright than if I block one side. Let me once more recapitulate what you've seen in the experiment. This is a Michelson interferometer. There's some light coming from here, going into the interferometer. It gets split into 2 parts. One part goes to the right, goes to mirror 1, and one part goes to mirror 2. And then the mirrored beams return, and they then overlap, and this is what you've seen on the wall. So now, if we have waves, you see that if 2 waves overlap constructively, that means they're in phase, and the phase is the difference between the maximum from one wave and the maximum of the other wave, then you get constructive interference and you get an even more powerful wave. So this corresponds to a lot of intensity. But however, if you phase shift one of the 2 waves such that they are out of phase, then always a maximum superimposes with a minimum, meaning that in total you get 0 as a result, and that means no intensity. So this predicts that light and light can actually give darkness. So here you see a nice animation where the relative waves are phase shifted, and you can see that sometimes you get an enhanced intensity, whereas in other times you get 0 intensity as a result. So what does interference mean for our Michelson interferometer? So you see, when we start with constructive interference, we send light in, it gets split 50%, 50% to the 2 mirror, and it joins together to give you 100% light intensity, leaving to the left, and that's what we saw on the wall. But then when we change the phase, we, for example, only get 50% of the light here. And we change it again, and then we get darkness here. So light and light via interference can give you darkness, and this is what you've seen in the experiment. You might wonder what happens to the energy. So of course we cannot violate the law of conservation of energy. So of course there's a second output that actually returns towards the light source. So you see here when there's not only transmitted light here with this semi-reflecting mirror, but also reflection light. And in this case, it turns out when you have darkness here, i.e. destructive interference, you get constructive interference in this beam path, which means all the energy returns towards the light source here. So, and on the other hand, if we have constructive interference here, we get destructive interference here. So therefore it's all fine. So now the interesting experiment was when we blocked this part with our hand or this little black piece of paper, then you see that now you cannot get destructive interference, and out of this 50% light, again 50% are transmitted, nothing interferes with it, which means 25% of the total energy end up on this side, and that is what we try to demonstrate in this experiment. So indeed, blocking light can sometimes make it brighter. So that's what we saw. Well, where is interference important? Well, it is used a lot technologically. So you see here an example of, in this case, a radar, so another frequency and an electromagnetic wave, where you can scan the surface of the Earth, and by the interference signal, you can then satellite-based conclude quite precisely what is the height map of this terrain. And from that, you can then even see changes in the terrain over the years and so on. So tiny surface deformations can be measured this way. Now we will look a little bit more in detail of under what conditions interference can happen and when you do not see it. Because as you know, interference is not necessarily an effect that we observe all the time in our everyday lives. So how comes? Well, the explanation to this is coherence. So we need coherent light to see interference. So if we have ideal coherence, we have to superimpose not the intensities, but the amplitudes. So that is the amplitude of the wave. Think of the water waves. If there's this oscillation between a maximum and a minimum, it's going up and down and up and down. And the same happens with the light. The electric field goes positive, negative, positive, negative. And so in this case, you have to superimpose the amplitudes, and then you have to take the intensity as the time averaged mean square of these oscillations. So you get, when you superimpose the amplitudes, you get this effect of interference, and you can see interference. However, if you are not coherent, then, for example, under ideal incoherence, and that's mostly what we see in our everyday lives, then we don't observe that. What you do is you superimpose the intensities, and that's what you then observe. So no interference is observable, and that's what you know from everyday life. If you switch on the light in your room and you switch on another light source in the room, it never gets darker, it just gets double as bright. So of course, you always have interference, but if it's different frequencies, then you have this beating of frequency, and in a few femtoseconds, essentially, something that was constructive becomes destructive and vice versa. So on average, on the time scales that we normally measure, we cannot observe these interferences, and therefore we have to sum up the intensities, because that is what turns out mathematically that you can express this as the sum of these averages. So we can try to quantify that. We can quantify coherence. So coherence is the capability to interfere. And we can do that by the correlation of wave fields. So you will certainly learn that later in your studies. And you can subdivide the topic of coherence into spatial coherence and temporal coherence. Sometimes you can also call this lateral coherence and this longitudinal coherence. So for example, a point source is spatially coherent to itself. And we will see that by an experiment that's demonstrated by the Young interferometer. And in the sense of temporal coherence, you have to think that the wave train, if it is monochromatic, it always has the same frequency, and therefore an earlier version of the same wave can interfere with a later version of that wave. And that only is possible if you're monochromatic. If you are polychromatic, then the wave train will always sort of change its frequency if you, or it has a range of frequencies inside, and that doesn't allow this interference of an earlier version with a later version, or it does allow that only for a small time difference, and that means a small longitudinal path difference. So if the longitudinal path difference gets too large, then we do not observe interference. And a way to see that is the Michelson interferometer. So if you try to do a Michelson interferometer with white light, then this will be extremely difficult to adjust, because you need to adjust the two path lengths to a precision of only a couple of wavelengths for this incoherent white light. However, if you try to do that with a laser, it's quite simple, because you have a long longitudinal or long temporal coherence length, and therefore it doesn't really matter whether you're wrong by 1 or 2 or 3 or 4 wavelengths. Here you see the temporal coherence of various light sources, ranging from a mercury lamp at high or low pressure, argon laser, helium neon laser, or a light emitting diode. So what is interesting is here that you see 3 different ways of characterizing the temporal coherence. One of them is the relative spread of the wavelength, or here it's the spread, well, not, this is the spread of the wavelengths, this is the spread of the frequency, and this is the temporal coherence length measured in meters. So you can interpret this as how far can you detune a Michelson interferometer to still observe coherence. So if we look at this coherence length, you see that the mercury arc lamp has a very small coherence length in the range of only something like 30 micrometer here, or 300 micrometer for a low pressure arc lamp. However, if you compare that to an argon laser, that's a lot longer. Here you see that's already 30 millimeter, or here we go to 10 centimeter, or with a stabilized laser you can get enormous coherence length here, for example 10 to the 6 meter coherence length. That means you can send this light for kilometers, many kilometers, thousands of kilometers, and you can still interfere the light with itself after this much delay. So that means it's a very, very precise frequency, and you see that the spread in wavelengths is extremely small, as is the spread in frequency. And in fact, there's even lasers that you can stabilize with some methods in the range of hertz, so that you can really even interfere different lasers with each other, because you can observe this. These fluctuations are then so low that you can observe them by eye. An LED is sort of in between in terms of white light sources, and it's a relatively good light source, but its coherence length is not very large, but also not the smallest. Of course, there's some white light sources which have coherence length in the range of only 1 or 2 micron, basically. We already said that in ordinary life, it's usually not easy to observe interference effects, because most of the time the longitudinal coherence or the lateral coherence is not good enough. However, there are some examples where you do see such effects. And I will give you a few examples below. Imagine now that we have a slab of glass or another material, maybe a film of oil or something like this, and light hits it, and we get reflected light and refracted light, and the refracted light is then reflected at the rear surface of the material again and returns. And as you see by this design here, if this is plain parallel plates here, then you see that the emergent light has the same angle from both reflections. So if we are longitudinally coherent, then you will see that we get nice interference effects between the two rays here. However, they are also displaced a little bit, so therefore we need a certain amount of longitudinal interference as well as a translational or lateral interference. So when these conditions are met, that means when the size here is small enough, then we will nicely observe bright and dark fringes. And if it's larger, then we will still see for a range of particular colors interference here, which will make the interference fringes appear to have colors. And we will see examples of this further. So here's a little bit more detailed picture, and you see that you can get, for example, even when they're not perfectly plane parallel, you get in certain areas, therefore, a bright fringe here and a dark fringe here when there's constructive interference of the returning rays with the ones that are reflected in the first material transition and a second one. So as you see in this example, it doesn't necessarily need to be a plate of glass, a very thin one, or an optically dense material. The same actually works just as fine for optically less dense material. And there's a nice example, as I will show you below, which are tiny cracks inside glass or another material, give you really nice interference fringes called Newton's rings. So here you have one example of such interference on an oil film on water, and it is thin enough in the range of wavelengths, and therefore we get the appearance of a dark fringe here at a certain thickness. So that's when the returning light has just half a period delay. And then we start to see all kinds of colors because, for example, in the blue one we get the blue being constructive, but the red and the green one being destructive, and so on. And then the colors with the thickness becoming thicker and thicker changes, and eventually you cannot really discriminate the colors anymore because there's too many close by wavelengths that constructively and destructively interfere, other ones right close by, and therefore we cannot see the colors anymore. And that is, of course, what we observe in everyday life. So actually this is diesel on water. So here's this example that I already indicated, which is a crystal that I saw in the Gustavianum in Uppsala University, and you see that it has sort of a crack inside, and it's tiny, and therefore you really nicely see these bright and dark fringes and the same sort of series of patterns. So the crack is very, very thin on this side and becomes thicker and thicker inside that crystal here, and you can nicely see these interference colors. So now we are going to look at this experimentally at Newton's fringes by pressing two glass plates together with a tiny gap of air in between. This experiment shows Newton's fringes. So for this we have a light source here, an aperture and a collimator, so that generates pretty parallel light here. And this is the most interesting bit, which is two parallel plates that are pressed closely together, and then we are observing the reflected light that through a lens we generate an image of these Newton's fringes onto the screen over there that you can see in the background already. So let's look in detail how this image looks like. You see nicely these fringes, and you see the colors which come from the fact that the different wavelengths have a different length, and of course, for the same distance between the glass plates, you get constructive and destructive interference for different colors. So you see the different colors and even the different orders if you look sideways, in the sense that this is 2, 3, 4 wavelengths delay, and then the colors become more pastel-like washy colors. So now I'm going to change here a little bit the pressure on the glass, and you see how I make these colors move because I changed the distance. So this is now a very small distance, for example. And if I go like this, I make it larger distances, like here. Sehr schön. We now continue this lecture by looking at two interferometers, the Young interferometer and the Michelson interferometer, and look at the effects of coherence and interference on the results that you see from these interferometers. We start with Young's double-slit experiment. This is a setup to demonstrate Young's double-slit experiment. Here we have a light source. Then we have a coherence aperture that makes the light source into an effective light source with a very, very small slit. I can vary the size of the slit by turning the screw, which I will do in a second. Then here we have a collimation, so that we get a collimated beam whose coherency depends on that aperture. And this, of course, is the most important part, Young's double slit. So this is a piece of brass with two very, very narrow slits closely spacing generated by laser engraving. Then what you now see is, without any optics, directly the far field of this Young's double slit. And this is filmed by a camera that you see over here. And so now we are going to switch to the camera, and we make it dark in the room that you can see the interference from Young's double slit with white light illumination and a relatively coherent beam at the start. So you can nicely see this interference. You can even see the slight color dependence of the interference pattern. And if you look closely, you can see sort of the higher orders of the single slit next by to this double slit pattern that forms these very closely spaced interference fringes. What I'm going to do now is I'm varying the slit aperture. So when I make the slit aperture wider, you see how these stripes start to melt together. Of course, everything becomes brighter. The higher orders from the single slit interference are more prominent because they're brighter now, but you see how with less coherence, the interference pattern that we're interested in the middle is actually starting to vanish. So this concludes Young's double slit experiment. So this scheme of the Young's double slit experiment shows you nicely why we get this series of fringes that are bright intensity, no intensity, darkness, brightness, darkness, and so on. And so the reason, of course, is that if the source is small enough, the light that travels from the source to one of these two slits goes here. So that's one optical path length, and this is the other optical path length. And if they are equal, for example, in the middle, you get a bright fringe because you get constructive interference of the light that took this path and the light that took this path. Whereas if you now move a little bit sideways, we have decreased this path length and we have increased this path length, and therefore if the path length is, in this case, half a wavelength, we get destructive interference here, and so on. And so we get a series of fringes by this effect. So we finished this lecture by the Michelson interferometer. Let's look what happens when we detune a Michelson interferometer. So this is a slightly more professional version of a Michelson interferometer compared to the sketch that you've seen before. So here's a source. The light goes to this semi-reflective mirror, let's say a 50% beam splitter. It goes to one of the two mirrors this way, returns, and then transmits here. And in the other case, it transmits first and then comes back here. So as you see here, what is different to the version before is that we have now this C here, which is a compensation plate. Well, think about what happens. The light transmits here, so it has to pass through this slab of glass, which we need to support this mirror surface here. And it has to do that once, 2, and then 3 times when it comes here. Whereas this one, if we didn't have anything here, it would just go once through this material. And therefore, we need an equivalent thick slab of glass here. And this way, then the beam goes through glass 1, 2, 3 times this way, and 1, 2, 3 times this way, and then it matches. So this is especially important if we want an achromatic performance. That means glass is dispersive, and we are going through glass here, and only by putting this compensation plate in at the right angle, we can actually make this interferometer really work for light, for white light. And tiny adjustments can be done by rotating this compensation plate a little bit, and we can adjust the relative amount of glass that this light here has to pass through. Roughly it has to be the right thickness, but tiny adjustment can be made this way. And so this way we can make a white light interferometer. So if we now have divergent light that comes from here, and what we then get is actually this sort of effect that there is, at the perfect optical path length being equal with the 2 paths here, with the compensation plate that is not shown here, then you see at a particular Z position, if we put a camera there, we sort of get nicely constructive or destructive interference over the whole field of view. But when we detune this mirror outside, then we start to see fringes, so that look like circular fringes this way. And so they are called hiding of fringes if we detune and we have divergent or convergent light here. For example, in monochromatic light, because otherwise we would quickly move out of the longitudinal or temporal coherence length. And there's another way to detune a Michelson interferometer, which is by tilting the mirror. And if you do that, you get what is called Fizeau fringes. So also imagine monochromatic light that basically instead of seeing rings on the screen, you basically see these stripes on the screen. If I tilt it in the other direction, of course, I will see horizontal stripes on the screen. This concludes the lecture of today, and we will continue with another lecture tomorrow.